Welcome to today's webinar provided by the Environmental Chemistry Division of the American Chemical Society. I'm Virendra Sharma, a professor at the School of Public Health of the Texas A&M University, and I'll be the moderator for this webinar. Please type your questions in the question box, and I will read this question after the presentation, which will be around 45 minutes. And later we plan to put at the website of the Environmental Chemistry Division this webinar that we recorded. And today's speaker is Professor Renyi Zhang. Renyi is a university distinguished professor of the Texas A&M University. Renyi has many research accomplishments and honored with many awards by the Texas A&M and also the professional societies. Zhang's research led to major breakthroughs in understanding chemistry of the formation and transformation of atmospheric aerosols, which represent a key contributor to air pollution, human and ecosystem health and climate. He used both experimental and theoretical approaches to elucidate the detailed chemistry of volatile organic compounds relevant to tropospheric ozone and secondary aerosol formation. And theoretical approaches, he not only used model, but also further improved the model to enhance understanding the atmospheric aerosols. In experimental strategy, his group invented analytical methodologies, including a shock tube and novel environmental chambers to investigate aging and variation in the properties of black carbon particles. Zhang research provided insight into the chemical mechanism leading to severe haze formation in developing countries. Results identified striking feature in formation and transformation of secondary aerosols under polluted conditions, which are characterized by two distinct processes involving nucleation and growth. Recently, his group revealed for the first time, explained the mysterious formation of pylic acidic sulfur particles during the historic 1952 London fog, but also unfolds the chemical mechanism for severe haze formation in China. Dr. Renyi Zhang, our speaker today, has impressive record of publication, including articles in Science magazine. With this brief introduction, I let Dr. Renyi Zhang to present the seminar. Again, to remind attendees, please type your questions in the question box for the question and answer session, and I will read these questions for Renyi to respond. So I give this to Renyi. Please, Renyi, start this webinar.
Thank you very much, Virendra, for the kind introduction. Because I'm presenting on the campus of Texas A&M University, if I don't say this, I will be in trouble. Okay, so I'm going to talk about the chemistry for the formation of urban fine particulate matter. First, I'd like to provide a brief historic perspectives about air pollution. So I got a few figures here. 1948, Los Angeles smoke, 1952 London fog, and 2006 Mexico City pollution, and also 2013 severe haze in Beijing. The question I like to raise here is that are those similar, and how do they form? And most importantly, what is the chemistry for each of those? We know that the Los Angeles fog is more photochemically driven, so normally forming in the afternoon hours and also in the summertime. So the sunlight is playing a big role there. Whereas the 1952 London fog is more aqueous chemistry driven by aqueous chemistry. The particles are highly acidic. And also we know that the situation in Mexico City is sort of similar to Los Angeles. So the question here is, what is the case for Beijing? And I will try to make my point here that I believe that the Beijing haze actually bear the characteristic of both photochemical smoke and aqueous fog. So now I got a couple of pictures here. Can you think which one is haze and which one is fog? And I cannot tell, but I actually have a trick that you can differentiate both of those. And that is, if you differentiate, the way you differentiate fog versus haze is not looking to how they form or by measuring the visibility, but you look how they dissipate. So the real fog will dissipate in the afternoon hours. We actually started with fog this morning in College Station, and by now it's completely gone. So no fog problems, no haze problem, and everybody can go safely to vote for Senator Ted Cruz or Beto O'Rourke. The other thing I also try to emphasize in my talk is that those two are also interchangeable. So fog can evolve into haze and vice versa. And we all know that fine particulate matter plays a very important role on human health. During the 1952 London fog event, and about more than 12,000 people died because exposure to toxic particles, and it is estimated about 4.2 million people died prematurely because PM exposure. So the question I like to ask here is, what is most lethal for PM 2.5? Is the mass concentration, so that's the amount of the PM in the air, or the chemical composition, particularly the toxin. And also, how about particle size? Normally, people believe that big particles will be deposited primarily on the lungs, whereas smaller particles can actually penetrate all the way to the other part of your body. And finally, how about pH? We know London fog is highly acidic, and was that a factor causing a major fatality in 1954? So here's a study that we're working on. It's a paper submitted to Proceeding National Academy of Science, and we developed an animal model and looked into how mice response to PM exposure, and we found pronounced immunosuppression. This is a project I collaborated with my colleagues from the School of Public Health, Zhang. And the other big issue about aerosol particles concerned with climate. This is the report from the Intergovernmental Panel for Climate Change. So you're looking at here is that on this side here, on the right hand side, so that's the warming to the climate, and on this side there's the cooling, and you see the greenhouse gases contribute to warming of the climate. Whereas if you look into aerosols, aerosol can either cool the climate by scattering, or can also warm the climate by absorbing. And also aerosols influence cloud formation, so that can also contribute to significant cooling. And the point I try to make here is that if you look into the IPCC report, and the aerosol radiative effect represents the largest uncertainty in climate prediction. This is just a paper published early this year, and looking into how ultrafine particles may have profound impact on convections and precipitations. And the first author, Jiwen Fan, was actually a former doctoral student of Texas A&M. So do we understand about the chemistry of PM? So I got a plot here, to show some ideas that this current understanding about PM. So particles, aerosols, or PM in the atmosphere can either form directly into, could be emitted directly into the atmosphere, and those are known as the primary particles. So alternatively, aerosols can also form from gases. So in the presence of sunlight, break up oxygen molecules to form ozone, and also excited oxygen atom react with water to form the hydroxyl radicals. And then the hydroxyl radicals can actually react with organic species such as volatile organic compounds or inorganic species such as sulfur dioxide. And this process here the oxidation process here may actually produce some gases, and they can actually form molecular clusters and eventually nucleation process to give a phenomenon that people normally refer as new particle formation in the atmosphere. So on the global scale, people estimate the contribution from new particle formation versus primary emission about 50 and 50. Of course, both of those nanoparticle, newly formed nanoparticles and the primary particle will undergo growth or aging process and eventually to give us the fine PM. And the other thing I also like to emphasize here is that the cloud can also have a profound impact on aerosol formation. Some gases can be taken up like cloud droplets, and when the cloud evaporates, that can also yield aerosol particles and etc. So there are different ways people try to put into this process into atmospheric models. The simplest way is you use a source proportion model to get some ideas about where the origin of those PM that you measured. And the problem with that is that it ignore the chemistry, transport and emission, etc. And people also develop very complicated chemical transport models to include all those processes. But the whole point here is that we still have very limited understanding about the chemistry leading to PM formation. First, I'd like to talk a little bit about how sulfate form. So I got some measurement here in College Station and also in Beijing. And normally people think sulfuric acid is mainly produced by OH plus the reaction between hydroxyl and sulfur dioxide. And we know this rate coefficient very well. And then you can write this fairly simple equation that predict your concentration of sulfuric acid dependent on the formation and also the sink. So the sink for sulfuric acid is mainly by condensation. However, if I look into my measurement in College Station Beijing, then I find out that there's a problem with my measurement here. And so roughly, if you see these two figures, and the sulfuric acid concentration are about equal. And I know that the OH concentration in both cases are about the same, and also the condensation of the sinks for sulfuric acid is also about the same. But however, the ISO2 concentration in College Station is about 2 orders of magnitude smaller than the concentration in Beijing. So somehow, if I use this equation, something is wrong. Nevertheless, you can do a very simple calculation to estimate the lifetime of sulfur dioxide simply by taking into account of the reaction rate constant and the hydroxyl concentrations, and you come up with this value here. Hey, ISO2 actually have very long lifetime. So if you do a very simple steady state calculation, that work. So the point is that if you generate sulfuric acid from OH plus ISO2 reaction, it's a very small process. So people have proposed various of aqueous pathways involving ozone, peroxide, hydrogen peroxide, organic peroxide, OH, and NO2. And what I like to argue here is that those do not work for the case of London fog because it happens when it's really, really foggy and there's not much light. And so that actually left over with this oxidant here, NO2. So NO2 can potentially oxidize ISO2. And in fact, there has been a couple of previous studies looking to increase ISO2 oxidation by NO2, and those are pretty primitive, using pretty primitive experimental approaches. And if you compare those two studies, then you find out those two measurements indeed has a lot of discrepancies that differ by 1 or 2 magnitude. One predict a pH dependent, the other did not. And the other thing you look at this reaction here is that so you would also believe this reaction will be strongly acid dependent because once you generate the proton will drive the reaction backward. And so the pH can actually play a very important role. And right now, we are estimating pH using thermodynamic models, very few measurements can verify those thermodynamic predictions, and there are all kind of complications in estimating the particle pH. And also both cases use bulk solutions, which may not be relevant to gas uptake. So to find out the problem for London fog, we actually did some very simple lab measurements. We got a test tube, and you expose those test tubes either filled up with water or with fairly dilute ammonia solutions, and we expose those to either ISO2 or NO2. Then we use a mass spectrometer to measure the amount of sulfate being produced. You see, in all cases, we actually can measure sulfate in the solution. And so this basically is the mechanism we propose: the ISO2 plus 2 NO2 to water, and that will give you a sulfate. And the case for London fog was that on the previous night, there was actually a true fog that happened. And it was wintertime, so people will burn a lot of coal, have a lot of coal burning. So that produced significant amount of SO2 and NO2. And those basically react on the cloud droplets. The size is about 20 micrometers, and then generate sulfur gas. And also, this turned out to be a very common industrial procedure to produce sulfur gas in large quantities. As I mentioned, London fog is not really a fog. I actually consider it a haze. And the point is that when temperature increases, and so all you're doing here is actually to evaporate water to form smaller droplets. Then those droplets become really acidic. So essentially what you're doing is that you have a conversion between the two sizes, and also there's a change with the pH of the particles. So when temperature is higher, the pH is very low, and when the temperature is lower, then it's mainly made of water. And the other interesting point here is that this kind of chemistry probably not going to work on fine particles, because if you look into the difference in the volume of the particles, 6 order magnitude, so the ionic strings are dramatically different. So this reaction can occur on cloud droplets, fog droplets, but they will not occur on fine particles, because the particle can be the ionic strings of this. So this basically is what we think the answer for the London fog problems. And this also turned out to be very similar to a process occurring in the stratosphere. So in the stratosphere, there's a stratospheric sulfate layer, also known as a Zhang layer. And so essentially, when temperature fluctuates, you see the particle become either concentrated or dilute. And by the way, this is actually a figure I got from a PhD dissertation under Professor Mario Molina at MIT. And I admire Mario not only because he won the Nobel Prize, and most importantly, I pick up chemistry from Mario. I'm not a chemist. I was not a chemist. I'm not a real chemist now, but at least I'm lucky that I'm working on some very interesting atmospheric chemistry problems. And this person here is Zhang, the developer for the aerosol spectrometer. I pick up a lot of knowledge from Zhang about the spectrometry. So now I'm going to talk about the London fog, the Beijing haze problem, showing here I have 4 panels. The top one here is the mass concentration of haze particles, and you see there are clean days, there are fluid days, and process repeat about 4 to 5 days. And this color here represents wind directions. So normally when there's a southerly wind, and the air in Beijing can be very fluid, whereas when there's a northern wind, the air can be very clear. And also plot on the second panel B, so that is a particle size distribution. So the particle diameter here from a few nanometers all the way to several hundred nanometers. And the contour here, the contours here is the particle number concentration. So what you can see from this figure is that the particle are pretty, on clean days, the particle are pretty small, and then on polluted days, the particle grow to larger size. And based on the size distribution, you can calculate the mean diameter of the size distribution. So particle is smaller than 50 nanometers, but by the time they grow, they develop into severe haze, and the particle become several hundred nanometers. The bottom one here shows the particle number concentration, how many particles per cubic centimeter. And you see on clean days, the concentration is very high, and that's because a lot of tiny particles form on clean days, and level off a little bit under the polluted scenarios. But those overall, the concentration is very high. So this is just a blow up of the two cases. So one case is from September 25th to 29, and the other is October 7th, October 7th. So I try to divide the pollution episode into different stages. I have a clean period, transition, and the polluted period. So nevertheless, if you look at on clean days, and this always happens in Beijing, and that is sudden burst of nanoparticles, and this is also the one I refer as new particle formation. Somehow, some gases actually suddenly form clusters and make to be new particle formation. So that happens every single day in Beijing when there's blue sky. And during the transition period, you see this takes about no more than a day, and you see the particle actually grow very, very rapidly. So you can start with the morning with clear skies, but by the end of the day, you can end up with very cool air, and so the mass concentration remains to be pretty high. So basically, in Beijing, you can divide this into either clean versus polluted. And on clean days, you could, because of new particle formation, produce very high concentration of nanoparticles. But those particles are very small, so those particles do not contribute much to the mass concentration of the particles. And on the polluted day, on the other hand, the mass concentration is very high, but the particle and also the particle size are larger. So if you consider the human health issue, so it's really going to be difficult to tell which one is more dangerous. Clean days, high concentration nanoparticles versus polluted day, the high mass concentration but larger particles. And this figure shows the evolution in the chemical composition during severe haze in China. Those are very nice measurements by aerosol spectrometer. You see from clean days to transition to polluted days. There seems to be a transition in the chemical composition. So this particles, representative particle size represented here. So clean days around 50 nanometers, 100 nanometers, 200 nanometers. And you see on clean days, the particles are made of primarily organics. The mass fraction was a very large mass fraction for organics. Whereas the inorganic ingredient appears to increase when the pollution develops throughout the event. So that may actually indicate that either photochemistry or aqueous chemistry plays a role at the different stages of the pollution development. I just like to mention very briefly about the photochemistry. And so here I got a compound, toluene is the most abundant aromatic compound. It's also very abundant in the urban atmosphere. A lot of studies being done to investigate the chemical mechanism for toluene oxidation. Most of the previous studies using the smoke chamber, and the conclude that if you have the aromatic ring here, OH will be added to the ring, and either going the 3 possible pathways, and based on chamber results, by measuring the final product, people speculate that this is a dominant channel and there's a minor channel here, but this is almost impossible. And so we have actually done recently a study that we actually come up with very different conclusions. So we believe that when OH added to the double bond to the aromatic ring, oxygen molecules most likely extract hydrogen from here, so that gives you crystal, and whereas O2 addition to the aromatic ring is actually negligible. And if that is the case, that may actually have a profound impact on ozone formation and also aerosol formation in urban cities. And our laboratory studies, are based on both experimental evidence and theoretical evidence. What you see here is that this is the potential energy for the 3 pathways for the reaction of the anode with O2, and this is impossible. And the most favorable channel we predict based on quantum mechanical calculation is actually the crystal law. And also we measure the products here is consistent. Here we use a chemical ionization mass spectrometry, and also this is turbulent flow conditions, so that eliminates wall loss. So now I'd like to talk a little bit about the new particle formation. That's a very pronounced phenomena in the atmosphere, occur in different regions, not only in urban cities. And people also find out new particle formation very frequently over forest. So this is how we normally define nucleation. And when you consider nucleation, it's basically a phase transformation process. First law, second law. So the enthalpy is decreasing, the entropy is also decreasing, and that's translated into a positive free energy. And so you're going to argue whenever you're going this reaction in this direction here, the process will not be spontaneous. And you can plot the free energy as function of particle size. If the system is undersaturated, so that's how you define the saturation ratio. So the free energy will increase indefinitely. That's never going to happen. If the system is supersaturated, there can actually be a maximum value when the process becomes spontaneous. So you can write the classic equation series of free energy has to do with the difference in the chemical potential plus the surface tension term, and then very easily you can calculate the size of the critical cluster. If you manipulate a little bit, you get the supersaturation for the critical side. So if you look into this equation, then you realize there's another problem here, because if the particle is very small, and the supersaturation is going to be enormous. So essentially, new particle formation in the atmosphere involves 2 barriers. One is the free energy barrier. The second is the curvature barrier, also known as the Kelvin barrier. So the real question here is, what are the species, organic species or inorganic species, can promote new particle formation? And there have been a lot of suggestions proposed: sulfuric acid, organic acid, or basic species such as ammonia and amines. This paper just got published early this year in Science. So they believe that in Shanghai, the sulfuric acid, dimethylamine, may actually play a very important role. And the first author here, the senior author of this paper, B1, was also a former postdoc at Texas A&M University. We have done many studies, and we believe that organics can also enhance new particle formation. And we specifically believe organic acid may play a very important role because they're prone to form hydrogen bonding. The other thing I'd like to talk about here is the growth process. So when particle nucleated, and then we see very rapid growth of particles. And how particle grow from organics, and this involves the formation of secondary organic aerosols. And there have been different theories being developed. So the typical pathways people believe is that when a volatile organic compound becomes oxidized in the air and the volatility of species start to decrease. So we start with VOC, then becomes intermediate volatility, with intermediate volatility, semi-volatility, low and extremely low volatility. So that's one approach. It's based on equilibrium partitioning between gas and particles. So alternatively, there can also be chemical reactions for compounds that are not so that are still fairly volatile, but they can involve in aqueous reactions or particle phase reactions. Here I show one case: alpha dicarbonyl involved in the formation of oligomers, and if that happens, it can also the oligomers may actually have some color to form brown carbon. And this is just a diagram that we think if you have a mesoglycol being uptake on water and undergo all those oligomerization processes to form oligomers. And we just have another paper submitted to EST, and we measure the optical properties for mesoglycol and mesoamine, and those solutions, those particles are really dark. So we believe those particles, the radial forcing can be comparable or exceed the forcing of black carbon. Now I'd like to talk a little bit about how sulfate form in Beijing, because the chemistry for Lunenfeld doesn't work for Beijing, because Beijing started with very tiny particles. So here are some measurements of sulfate in Beijing. In the particle, you see clean transition fluid. And on fluid scenarios, the sulfate concentration is very high. And you can certainly see this mass fraction here. And plotted here is actually the molar ratio of sulfate to SO2. And you see this conversion seems to strongly dependent on relative humidity. And below here shows the concentration of SO2 from clean to fluid, NO2, and also ammonia. And also the relative humidity here. So what we believe is that under fluid conditions, and because the pH is very high, and the aqueous chemistry can actually play a very important role. And subsequently, we actually performed some laboratory measurements. It's an environmental chamber. We did some very straightforward measurements. We introduced monodispersed particle with a similar diameter, with similar size, and those are made of oxalic acid. And then we expose the particles in the chamber to those different gases. And what we saw in our measurement is that if we have to have the right combination of the gases. If we miss out one of the gases, and we never see any particle growth, and we never saw any sulfate formation, and we use again mass spectrometry. So that's very different from the scenario of the test tube. In the test tube, we always saw sulfate formation, but not for the case of particles. And so we really have to have the combination of SO2, NO2, and ammonia to promote the sulfate formation. And also, so we use this equation to try to derive the uptake coefficient. That's the value people normally use in atmospheric models. And so we estimate that based on the field measurement and also based on the lab measurement. And those are more or less inconsistent. So this is basically what we propose for the Beijing case, because Beijing case really started with gases involving nucleation and new particle formation, and those particles are very small, so you can have few reactions, but very quickly the particle becomes very highly acidic and concentrate, and that actually inhibit this oxidation unless you have ammonia present. So essentially, this reaction can only happen when there's in the presence of ammonia to neutralize the acid. In fact, we also measure the ratio of positive ions and positive ions to negative ions, and we see that clean fluid, transition fluid, those ratios are very close to unity, suggesting that the particles may not be terribly acidic. So now I'd like to talk a little bit about what is the chemistry involved to produce the severe haze in Beijing. Essentially, there are two processes: photochemistry that will produce new particles, and photochemistry will also promote the oxidation of VOCs to a less extent for inorganic species such as SO2. However, during the evolution of haze, you see clearly there's a decline in photochemical activities, and this line marks the red lines mark the photolysis rate constant for NO2, so become very, very small when the air becomes foggy, but you still see this process keep increasing. So we believe that at a certain stage, you actually have a transition from photochemistry to aqueous chemistry, and the main driving force may actually be something like Linden fog. So if I consider the crucial problem in Beijing, I would think in early days, the haze has the characteristic of Los Angeles fog, and on the cloudy days, and the haze more has a characteristic more like Linden fog. It is also my belief that the photochemistry probably not going to give you very high mass concentration of PM. And, on the other hand, the aqueous chemistry can really push everything into the severe haze. So now I'm showing a comparison of chemical compositions among 4 different cities. The one thing I like to point out here is that, so if you look into the PM particle, the ingredients are very similar among the 3 cities: Houston, LA, and also Beijing. And although the annual average concentration is much higher in Beijing compared to Houston and LA, and there's some differences for Mexico cities. So what I believe here is that those are representative of the typical urban particles. Has a lot of traffic ingredient there with some background isotope. So now I try to do a comparison between Houston and Beijing, and I try to prove that this figure here is not only politically correct, it's also scientifically sound. Okay, so the population here between Houston and Beijing, and how many cars are in there, and those are the emissions. So what we did here is we use a very unique setup here to see how quickly particle grow under the scenario of Houston versus Beijing. So this is a chamber developed by my colleagues, former colleagues from Collins, and is now at UC Riverside. So the idea for this chamber is that there's a membranes here, so the membranes will fill out particles, whereas let gases in. So essentially, what you're getting is you're getting air, and because it's transparent, so you also have photochemistry. And so in this chamber, you have a particle-free environment. Then you inject your own particles and expose to those gases, and those gases oxidize, and then to see how the particle grow and how the optical property evolve. So we did the measurement in Houston and also in Beijing, and there's a comparison. So this vertical axis here is the delta the difference in the particle radius diameter. So we inject in both cases about 100 nanometer black carbon particles, subparticles, and we watch those particle growths. You see in Beijing, the particle grow very, very rapid. A few hours, the size almost been doubled. It take a long time in Houston for the particle grow to 30, 50 nanometers. So those growth rates are very distinct between those two urban cities. The other thing we also measure here are the light absorption enhancement. So that's the initial absorption versus the final absorption. And you see in the Beijing case, and the light absorption really get doubled by a factor of 2.5, whereas in Houston, it really doesn't happen much. And so what we believe is that, so because in our case, we introduce 100 nanometer black carbon particles, so the first stage for this process is there's a morphology variation, and particles become more compact and spherical, and eventually start to build up the coating. And so when light goes through here, after it gets focused here, that is before it's a lensing effect. And so it takes longer time in Houston, much longer time in Houston than Beijing to reach light absorption, significant light absorption enhancement. And the other point I'd like to mention is that once the particles absorb too much light, the air becomes very, very stable and virtually trap most of the proteins close to the surface. So that can have a major impact on the development of air pollution. And also, we know that black carbon is a big contributor to the climate, and this is a commentary by on our paper, and we suggest that there can be a big impact because the aging of the transformation of black carbons. So in this paper, we concluded that mediation in black carbon emissions achieve a co-benefit in simultaneously improving air quality and protecting climate. By the way, the first author, this article is a postdoc of mine right now, Zhang, just recently received the WMO honor. Okay, so now I try to compare the differences between Beijing and Houston in terms of the gas pollutants. So on the left is Houston, and on the right is Beijing. So if you look into sulfur dioxide, nitrogen oxides, and aromatic hydrocarbons, and those are consistently higher in Houston, about a factor of 10 higher in Houston than in Beijing. And this is a recent publications. So this paper suggests that in China there can be some highly reactive oxygenated hydrocarbons with very high reaction rate. You see the concentration of this pretty high, very, very high. This is in Nanjing, can reach up to 1 ppb, whereas Beijing is 700 ppb parts per trillion. This compound here, ACAC, can have very rapid chemical reactions, either can produce ozone or contribute to secondary organic aerosols because the compounds misoglycol and acetic acid are predicted as a major product of this oxidation reaction. So now we like to think about what are the sources for pollution in Beijing. As I mentioned before, people normally use the source apportionment method, and here's a paper using PMF, positive matrix fracturation model. And so what they concluded here is that traffic only contributes to about 3% of the PM, to a PM 2.5. And personally, I think this is way too small. And by the way, that's not me. also is unrelated. All right, so we know a lot of big cities in Beijing are very extremely congested. And also we know that there's a lesson that Chinese can learn in terms of improving air quality. So again, so this is in 1948, Los Angeles fog, and it's the present day Los Angeles fog. And back in 1948, a lot of cars, a lot of smoking cars. And as a result, so there's a very strict emission check for automobiles, and as a result, you see major reductions in nitrogen oxides of organic compound, and particularly those aromatic hydrocarbons. So that's basically only by improving car emissions you can achieve this effect. So to conclude, I like to just quickly mention some challenges we're facing concerning air pollution. Atmospheric aerosols have profound implications on human health, climate, ecosystem, etc. I quote this statement from the latest report of the National Academy of Science. So the title of this report is "The Future of Atmospheric Chemistry Research: Remembering Yesterday, Understanding Today, Anticipating Tomorrow." And so in this very nice report, they prioritize research areas. The top one here is to advance the fundamental atmospheric chemistry knowledge that enables predictive capability for the distribution reactions and lifetime of gases and particles. And personally, I see those important challenges and what promotes new particle formation, what promotes the formation of secondary organic aerosols, and what promotes the formation of brown carbons, and what is the cloud chemistry, heterogeneous chemistry. And there are still some challenges when people do lab studies and field measurement challenges. It's very difficult to measure those chemicals, particularly the speciation, those for nanoparticles, molecular clusters, all the way to submicron particles, particularly for organic species. And atmospheric models right now have a huge problem to represent the chemistry because we do not understand the exact chemical mechanism. I would argue this is one of the biggest contributors to the uncertainty when people make climate projections, and of course, so that's because the aerosol radiate forcing, and also there's issues with human health. So I'd like to stop here, and I would be happy to take some questions.
Thank you very much, Renyi. It's really very much detailed explanation in short time. And I really also thanks the attendees. They were willing to stay there. We have some issues in the background. We try to solve, and again, we apologize if there's some places it really bothers you. So there are a couple of questions, Renyi, that I get across, and I'll just at least few questions. So we start with this, whatever time we have, around 10 minutes, 11 minutes. One attendee is asking, you mentioned several factors, chemical composition, diameter, pH. What is the really driving force among these? Any dominating one, or all are contributing? If you can little bit expand your presentation or discussion on this point, please.
I think you're referring to the impact of PM on human health. Is that correct?
Yes, yes.
Okay, yeah, right. Yeah, I think there can be a lot of factors, and people even run models to predict the global fatality because of PM exposure. And I think my point here is that there are many factors that contribute to to the health effect. And personally, I believe that the mass concentration, chemical composition, size, and also potentially pH. The other thing is that right now we have very limited understanding about how those different factors contribute to human health. One question I like to raise here is that in 2013, the severe haze in Beijing lasts for more than 15 days, where London fog only lasts for 5 days. And the level of the mass concentration in both cases is almost comparable. And then you're going to ask yourself the question, how many people die from the two cases or equivalently? I would think London fog, there's a lot more people dying from 1952 London fog compared to the pollution problems. The other thing I think I try to illustrate is that those two type of aerosols have very distinct pH. So one is highly acidic, the other is almost neutral, weakly acidic.
Thanks, Renyi. One question pointed out, we do have in atmosphere hydrogen peroxide and some metal catalysis there. And what is your opinion? Do they have any role, or it's just we don't know, or just throw some light on this, please?
I think you're referring about the conversion of SO2 to sulfate.
Yes.
Yes. So traditionally, we believe that the conversion from sulfur to sulfate is mainly by OH radicals, and but this process here is fairly slow, as I demonstrated from my measurement of sulfuric acid in Beijing and College Station. People propose different variants of aqueous chemistry on cloud droplets, foam droplets, or even on aqueous particles involving ozone, peroxide, and etc. So I think the point here is that in the case of Beijing, and the severe case in Beijing, the ozone concentration was exceedingly low. So the ozone concentration was only about just a few ppb, and then you probably can eliminate those oxygen, the photochemically produced oxygen. The dust can play a role, but in the case of Beijing, we know the particle normally evolve from few particles to big particles. So in that case, the dust probably does not play a major role to produce sulfate.
Okay, thank you. And this is as a general question or general thought. We learn what happened in LA, and now we figuring out in Beijing and these factors. And now I think is a big environmental issue is New Delhi, India. So you like to say a few words or give your thoughts, what they can learn from your studies, basically, to avoid really severe problems right now in Delhi?
Yes, I think last year there was a publication in scientific report. So the study utilized satellite observations of sulfur dioxide, and they look into the level of sulfur dioxide on the global scale. And what they found out is that the emission, the SO2 level has been continuously decreasing in Beijing, whereas continuously increasing in Delhi. So now India actually become a superpower in terms of SO2 emission than China. So that could have enormous implications in terms of severe haze formation in India.
Okay, thanks. And if you have, one is just asking very general questions. If you have to give solution to government of those countries, especially developing countries, is there any solution, or they just need to start from scratch or change their lifestyle, or any engineering solution, or just so very general questions. We'd like to hear from your thoughts on that.
My take on this is that there's still a lot of work need to be done in the scientific community to really understand the contribution of the different sectors of sources. So people still arguing whether traffic is a big contributor versus industrial, and a lot of times people arguing about Beijing's haze is more caused by transport from other industrial regions. We just show the chamber study, you can see very clearly Beijing's haze, the haze in Beijing doesn't need any transport from other regions. Particle grow very rapidly, even under conditions that people consider traditional clean conditions. So there's this lot of gases. So to develop effective mitigation policies, my recommendation here is you really have to understand the process, the chemistry process.
And one of the question is just, I think is maybe more philosophical questions. Maybe it's possible that big particles first form and then go to small particles, or it is other way around?
Sorry,
let me repeat. The question is there any possibility that big particles forms first and then go to small particle or decompose into small particles?
I think that's very unlikely.
Yeah, this question is asked, so I thought just to get some of your views.
Right. No, I think that's highly unlikely.
Okay. And last two questions, or maybe this is the last question based on our time. You mentioned the role of ammonia a lot in your presentation in Beijing, and then maybe the amines are coming in other part of. So what is really, this is the de facto, right? And maybe wants to get more clarification from your presentation on this part.
Again,
ammonia means, what is the ammonia role that you have? They want to get a little bit more description or explanation role of ammonia here. Then we have sulfur dioxide and
right. Okay. Yeah. So I really believe that the haze in China is not very acidic, and the main reason for that is because the neutralization by base species such as ammonia and amines. So those particulate amines are stronger, has stronger basicity, so they can have even larger impact on the aerosol chemistry. Right now, there are very, very few measurements of amines in China. So this nice science papers and my former postdoc, Wang, actually did some nice work in Shanghai. And but those measurements are not very common. So there's still, we need to know more about the sources of those base species and also their atmospheric abundance.
Oh, okay. And we have 2 minutes, so I'll keep asking questions because you're still seeing questions. What is the residence time of these particles? There's one question is there.
So the residence times depend on the particle size. So big particles is very short residence time, where small particles can have very long lifetimes. And the other aspect I like to mention here is how particles are removed actually involves the precipitation. So cloud can be very efficient in terms of removing particles. So normally, you think about the weather system, so that normally takes 4 to 7 days. I mean, for like a front passing through, and so if you consider precipitation as the main removal mechanism for particles, so that's going to take about 4 to 7 days. So no more than 7 days, I would say, under typical scenarios.
Well, this is basically time is over here. So I'd like to thank once again Renyi and all the attendees. And regarding his presentation, we're going to put, this is our first ACS Environment Chemistry Division webinar. We are going to put online audio recording of this presentation. And you can also search through some of this one. You will see some references because a couple of people last year can get more information. So from this presentation, you can see some references there. So you'll get all the information. Again, thank you, everyone, and especially Renyi. Appreciate your time, and presentation is excellent. And this concludes the webinar. And have a very good day, everyone.